Okay, question 7 says, consider this series where we're summing negative 2 to the n over n factorial, and n starts at 1 here. So in expanded form, this is negative 2 plus 2 squared over 2 factorial minus 2 cubed over 3 factorial, and so on. And part A says, how many terms must be summed to be sure that the remainder is less than 10 to the negative first? How about 10 to the negative fifth? Okay, so this is an application of what we saw in the last video, right, where we prove what's known as the alternating series estimation theorem. And recall that it says that if I approximate the exact value of this series with a partial sum, S sub n, like let's say I add up the first 3 terms of this series to give us an approximation to the exact value of the series, the alternating series estimation theorem says that the error, which is just the difference between the exact value in your approximation and absolute value, can be no larger than the first discarded term. So if I use the first 3 terms, okay, the error can be no larger than b sub 4, right? This would be the first discarded term there. All right, so now let's go ahead and apply the theorem. So b sub n is 2 to the n over n factorial. b sub n plus 1 is then 2 to the n plus 1 divided by n plus 1 factorial. And so this theorem says that our error can be no larger than b sub n plus 1. So it can be no larger than 2 to the n plus 1 over n plus 1 factorial. All right, so now what I'm going to do is just use a calculator. I'm going to punch in a few different values of n and see what happens to this term b sub n plus 1. And by the way, I just used Desmos there. You can just add a table is how I did that, and put in n in the first column and then your expression for b sub n plus 1, and this quickly will generate for you the various values of b sub n plus 1. Okay, so I've included them here, and as we see, as n increases, b sub n plus 1, which is acting as this upper bound on our error, is decreasing. And that makes sense, right? Because the more terms we use, the better our approximation should be, right? And since our error is always going to be bounded above by this term here, right, that's saying, yeah, our error will be shrinking and will approach 0 in the limit as we let n approach infinity. All right, so now for part A, again, it says how many terms must be summed so that the remainder, in other words, the error, is less than 10 to the negative first. So just going down this column here, what's the first value of n so that the remainder is less than 1/10? It's right there, right, when n is 5. And so that means I'm going to use the first 5 terms of our series, in other words, s sub 5, and when you compute that, you get negative 0.9333, and the 3's just continue, okay? So if I use the first 5 terms of this series as my approximation, I know that the error in my approximation is less than 1/10. Okay, how about 10 to the negative fifth? Well, again, just going down this column, what's the first value of n where this b sub n plus 1 drops below 10 to the negative fifth? Now, at n equals 10, right, this is 5.13 blah, blah, blah times 10 to the negative fifth. So this is not quite there. It's at n equals 11 where we jump below 10 to the negative fifth. And so that means I'm going to have to use the first 11 terms of the series, okay, to guarantee that the remainder is less than 10 to the negative fifth. So s sub 11, when you add that all up, you get negative 0.86467, blah, 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 okay? Now, for part B, it says estimate the value of the sum with an absolute error less than 10 to the negative first. Well, I've actually already done that here. So part B is really asking you just for this number right here. We know that if we use the first 5 terms, then that error is going to be less than 1/10. So there's our approximation, and we know that that's going to be within 1/10 of the exact value. Okay, now as a side note here, we'll be able to show in chapter 10 that the exact value turns out to be e to the negative second power minus 1, which is about negative 0.8646647, blah, blah, blah. Okay, and notice our approximation when we used 11 terms, it's negative 0.86467, blah, 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 right? Pretty darn close. It's going to be within 10 to the negative fifth, right? All right, well, very good. That's going to do it for this video. In the next video, we will look at another example illustrating how to use this estimation theorem. All right, thanks.